Doug Witherspoon, CEO and Chief Scientist of HyperJet Fusion. Thank you so much for having me here to your lab.
Thank you. Glad to have you here.
Yeah, it's a real cool space. We're out in, what do you call it, Fairfax, Virginia?
Well, it's Fairfax County. We're in Chantilly, Virginia.
Chantilly, Virginia.
Yeah.
And I mean, you guys are working on very interesting technology, and we mostly focus on fission on this show, but we're fans of all nuclear technologies.
Okay, good.
So it's awesome to be able to explore fusion a little bit with you. And your specific style of fusion is this pulsed fusion. Is that what you call pulsed?
Well, no, we actually call it is pulsed, but we call it plasma jet magneto-inertial fusion. Plasma jet driven magneto-inertial fusion.
Jet driven magneto-inertial fusion.
Right.
All right, well, we'll get into that in a second. But first, I want to hear a little bit more about you. What's your story? How did you get into this type of technology?
Well, when I started out after grad school, I worked for a small company that wasn't too far from here in Alexandria, GT Devices, and that company was interested in doing something called impact fusion, bringing high velocity projectiles to impact a target and make fusion energy out of that.
Physical projectiles?
Yeah, physical projectiles.
And what would be the materials and the projectile and the target?
Well, the target would have deuterium, tritium fuel inside a metallic cavity. And the projectile would be some kind of solid slug of metal with some plastic sabot around it.
And then what's the idea behind this impact fusion? After you slam into your target, how do you capture the energy out of that?
Well, what you have is a driver that accelerates this projectile into the middle of a large chamber where the target is located. That when the projectile hits the target, it will fuse if you have enough velocity coming in and you have the right target design. It will create fusion energy. And so you get just this tiny little micro explosion, if you will, kind of like laser fusion, except you drive it a little differently. And the energy comes out and is absorbed in the walls of the chamber.
Absorbed as heat?
It's absorbed as basically as the kinetic energy of the neutrons and other particles coming out. And so that gets absorbed in a blanket and in a fluid that then transfers that to a heat transformer, which makes steam, which drives an electric generator.
Cool.
Yeah. That's the idea.
So that's what you were working on. What happened?
That's what we were working on then. Well, we discovered that the high velocity was hard to get.
Yeah. And how high velocity did you have to achieve?
Well, you needed to get into the 10 to 20 kilometer per second range to get that.
That's like escape velocity style.
Yeah. So it escapes around 11.4 or something. So what happened then was the company changed its focus and started developing the technology for hypervelocity guns, actually for the Department of Defense. And so we were kind of a big part of the Star Wars era back in, this was the mid-80s to early 90s. And so we were developing technologies for capillary discharges and rail guns and things like that can move projectiles at very high velocities. Eventually, that company was purchased by General Dynamics Land Systems because they wanted to use the electrothermal gun technology that we were developing to upgun the M1 tank, to put a new gun, a new generation of gun.
Railgun weapons.
Yeah, and this was in '89, and shortly after the buyout, the Berlin Wall fell, the missions evaporated.
Good timing to sell a company.
Yeah, it was a good timing. And so anyway, I went off with, a few years later, a partner and I went off and we started another company called Utron, which was located out in Manassas. And we continued developing an offshoot of that technology called the combustion light gas gun, which was invented by Derek Tidman, who was the president of and founder of GT Devices. And so we won some contracts from the Navy and BMDO to develop that technology, mainly for initially for missile defense. But then ultimately the Navy got more interested in using it for onboard ships. Now that technology was developed over almost 15 years or so, and eventually kind of fell out of favor because they really wanted to push the railguns in the Navy, and so that's where all the development went. And so that program basically died. Must have been 10 years ago or something like that. But in the meantime, while I was there, we started doing other work. I started developing ideas for using pulsed plasma discharges for materials applications.
What kind of materials applications?
Well, like for making metallic powders.
For like 3D printing or something?
Yeah. Although at the time 3D printing didn't really exist so much. It was just the early days of that. So that market really wasn't there, although it is now. Yeah. But other things like thermal spray and dynamic compaction, which is a process for taking metallic powders and compacting them into a part, like a press.
Yep.
And so that worked. That process worked. It was all patented. And in fact...
So how does that work? You've got your powders, and then you've got a mold around it. And that mold, when it is compressed, will end up at the shape of the part that you want.
It'll end up either with the shape you want or close to it. Usually you have to do a little bit of finishing. On the part.
How does the plasma, though,
That did not use plasma.
Oh, I see.
That used the combustion-like gas gun technology. So what you did was you had a large chamber, a modestly large chamber, filled with a high-pressure mix of hydrogen and oxygen. And then you would ignite that in a special way to make sure it didn't detonate. And then that would push a piston, which would push on the powders and compress that to make a part. And then you would take that part out, and that was in a green state, and then you would bake it basically in a furnace to make sure that everything consolidates properly, and then you have a part.
I see. So it's almost like a dynamic forging process.
Exactly. Yeah, that's exactly what it was. But it had some real advantages over typical processes where you use kind of a hammer press or something, because this could do a slow, on a time scale that was a little bit slower than the existing technology, and didn't introduce the shocks that caused some damage to parts. And you could get much higher pressure. You could almost double the total tons per square inch. And so Utron continued. I left Utron in 2003 because I wanted to go back and do fusion. And
why? What drives you to fusion? Why is that important to you?
It's a good energy source. Always has been. I mean, that was what I did my thesis on back in the 80s, early 80s. And so I wanted to do that. But what happened was they continued on with that dynamic compaction, and they actually make parts for some Navy missile. So it's pretty cool.
So you wanted to get back to fusion. So what did you do?
Pardon?
What'd you do?
Oh, I'm sorry. Well, I left Utron and I started HyperV Technologies.
And what was the idea? What was the kernel of insight that?
Well, that's kind of hard to say. I wanted to get back into the fusion research area. I wasn't sure quite what I was going to do at the time, although I knew that it was going to be something to do with hypervelocity, which is why I named the company HyperV Technologies. Because I knew how to make things move fast. Plasma jets, projectiles, things like that. And so what happened then was there was this idea that a scientist at DOE had, Francis Theo, for this plasma jet magneto-inertial fusion, PJMIF. And he had some ideas he had been developing with some other people for a number of years on how to make fusion with these imploding plasma jets. And I thought that was a really cool idea. And he had some neat ideas on how to develop the plasma gun that would be the driver for doing the PJMIF, because there weren't any guns available at the time that could do that job. Because you need to get a lot of mass moving at 50 to 100 kilometers per second.
Wow, so that's even faster than we were talking about.
Oh yeah, yeah. But there's no solid projectile. It's all just plasma.
Well, hold on. Help me understand that a little bit better. So you've got mass somewhere.
Yeah. Well, it's like the mass in a gas. There's mass there. All right. So
what gas is this? What is the?
Well, ultimately, you'd probably use something like xenon because you want a very heavy mass or heavy molecule to drive the implosion process.
And xenon is very because it's heavy for a gas and also inert and
inert, right? Yeah. But xenon is expensive, so we don't work with that. We work with argon, which is relatively cheap.
Right, using welding, super cheap.
Yeah. And so we use argon, and we design guns that have very fast gas valves that will inject the gas into the area where you start the arc for the gun. And you do that on a very fast time scale, just a couple hundred microseconds or so. And then you ignite that, and then the current and magnetic forces accelerate that plasma down the plasma tube. And
the magnetic forces that are born out of the plasma, you don't have external magnets hooked up to?
No, there's not external magnets, but what we do is we drive current through it. And the current interacts with its own self-generated magnetic field. It's called a J cross B force. J is for the current density, and B is the magnetic field that's generated by that current. And that J cross B force is in such a direction that it accelerates the plasma.
That's the
way a railgun works.
J cross B. So this is it when I put my fingers up like this?
It's the three finger rule.
Yeah. So walk me through this 3-finger rule again. So you got. What are the 3 fingers?
The 3 fingers are the direction of the current, the direction of the magnetic field, and the direction that the force goes.
And so what you want is the force is your gun. That's what's shooting.
Well, the force is in the direction that you're accelerating the plasma.
Right.
So the current is perpendicular to that, and the magnetic field is also perpendicular, but in another direction, okay?
Got it.
And so the cross product of those 2 vectors is in the direction that you want to accelerate the plasma.
And that's how you get your plasma to your 100 kilometers
to the high velocity. That's right.
Awesome. And then the idea behind this entire fusion system is you've got a sphere with a lot of these guns planted around the sphere.
That's right.
And if you inject enough, eventually xenon, but let's say argon for now, from all different directions, you've created a gas plasma collapsing shell that applies a ton of force.
We call it a liner. So, I mean, the liner would be yay thick, say, and then just imagine that it's an annular shell.
Yeah.
Okay. And that shell is rapidly moving towards the center. It's collapsing and imploding.
And how do you keep it a perfect spherical shell as it implodes?
Well, you set up the initial conditions so that it starts out as smooth as possible. Once you make that shell, it'll do whatever it's going to do.
Yeah.
Right? You don't have any control over it other than what you set up in the initial conditions.
And how many guns does that require then for your shell?
Well, the experiment we're doing now is to do 36. But for a real reactor, you might need several hundred guns, maybe up to 600.
And the experiment
maybe only 300, but we don't know the exact number yet. But it's in that order.
And the experiment that you have right now is a couple meter bubble across?
It's a 9-foot diameter vacuum chamber.
Okay.
And it has 60 ports on it.
Yep.
We can put up to 60 guns on that chamber, and eventually we hope to do that. Right now, we're doing only 36 because that's all the money we have to do. And then our hope is next year the program will go to a follow-on program. And then we hope to add more guns to fill out the remaining ports.
And the fuel is supposed to be in the center of this. How do you get the fuel to stay in the center of this 9-foot vacuum bubble?
Well, it's inertial. So what happens is you would have a subset of those 60 guns that are equally distributed, okay, or uniformly distributed, maybe 12 guns. Those 12 guns will fire first, and they would form a pre-liner that would collapse on the center.
And what are they firing?
Well, they would be firing ultimately deuterium and tritium.
And different guns for deuterium, different guns for tritium. What's the
No, it'd be a mix of deuterium and tritium, presumably.
In what form?
As a plasma.
Also as a plasma.
Also as a plasma. It would be very similar to the plasma guns that we used for the liner, except it would just be accelerating a deuterium tritium plasma.
Got it.
So that would fire towards the center. It would then collapse into a little ball of plasma. And that ball of plasma would last just long enough for the follow-on real liner to collapse on it. So the time scale for this is microseconds. So you would fire the fuel guns, right? And then just a few microseconds behind that, you would fire the liner guns. And so that liner would be racing right behind the implosion of the fuel liner.
Yes. And just microseconds? Because it sounds to me, if you're firing at that high velocity and you've got this plasma, if this plasma isn't perfectly balanced when it comes together, it's going to move in some direction out of center, right?
No. If everything is uniformly targeting at the center, it would just collapse on the center and stay there. But if you didn't do anything else, then that little ball of plasma would expand back. It would bounce back.
And you have a couple milliseconds
it's hot.
To get that
It's hot.
Yeah.
And there's a lot of pressure there.
Yeah.
And so obviously it's just going to start expanding again. So what you have to do is catch it and with the following liner right before it starts to do that.
Okay, so now you have your liner collapsing in on your plasma of your fuel, your deuterium tritium fuel, and it creates a fusion. How much? What mass of your fuel is inside there? It's more than one deuterium or more than one tritium, right?
I mean, you have a few milligrams. It's not very much.
And then what percentage of that gets fused, and how much energy does that release per pulse?
Well, I don't remember the exact number for how much gets fused. That will depend on the final conditions, but a substantial fraction of the deuterium tritium fuel will fuse.
And then how much energy gets released in a pulse?
That will depend on how the reactor is designed in the final analysis. But imagine, if you will, that you have something that's firing at about 1 shot per second. And with that, depending on how you do your guns and the masses and everything involved, you can have an average energy output that can run anywhere from 50 megawatts average up to a gigawatt average power.
Wow.
And thermal energy coming out.
Well, that's what I was going to ask.
Yeah, and then you have to convert that to electricity. So
eventually it's thermal. What is the actual literal form of the energy in a deuterium tritium fusion event? Is it a neutron with kinetic energy?
Most of the energy is in neutrons, right? And alpha particles.
And you can't convert the alpha directly to...
Well, you could convert the alpha directly if you had a magnetic field that you could interact with. But that's not going to be easy to do because most of the energy comes out in deuterium tritium as a neutron.
Okay.
So you have to do that in a thermal blanket, absorb the kinetic energy thermally.
Love it. What is this thermal blanket, and are there materials concerns? I guess... So the thermal blanket will sit outside of your vacuum, obviously. And then I guess because you have to maintain a vacuum over a big area, you've got pretty strong walls to begin with that separate your vacuum space and your blanket. Because I was just thinking,
and the outer atmosphere.
Because you're going to have a lot of neutrons blasting through that. You need to be pretty strong material. Because there's material concerns whenever you've got neutrons moving, right?
Well, yeah. I mean, ultimately, you'll have issues of neutron embrittlement of the steel and structure and stuff like that. So, these things will last for some period of time, and then you have to replace them.
But it's not as big a concern, let's say, for like a tokamak where the material, where you also have to create a magnetic field in that same space.
Well, the materials issues are similar in the sense that neutrons affect everything.
But I guess what I'm saying is you get to build a thicker wall than they do.
We have a little bit more freedom in design of that wall than they do. Because we don't need the toroidal magnetic field that a tokamak has.
Right.
That's a real complication.
Right.
But they have other systems that they're looking at, stellarators, that don't require those huge magnetic field coils.
They have
different. Well, it uses a twisting magnetic coil structure that doesn't require a toroidal current structure. I mean, a toroidal current to do the confinement. It's more of a static field.
But those are further off in the future, even than tokamak.
Well, no, they're working on them now. I'm not personally that familiar with them, but they're making good progress on them from what I hear. The Wendelstein 7A, there's some other acronym for it, in Germany is making really good progress on the stellarators.
Awesome.
But
that's a different technology.
That's a totally different technology.
Okay, so you've got, all right, so we created your fusion event, once per second pulse. Now you've got your neutrons and alpha particles being kicked off. They hit your blanket, turn into thermal energy, and then that's just hooked up to some sort of simple steam cycle to get...
Yeah, it goes through like a molten salt or something that... absorbs the energy and then cycles through a heat exchanger, which turns water into steam and then drives a typical
since
generator.
You guys are doing this in pulses and you don't have to maintain since you're doing it in pulses, you get to evacuate the result of your fusion event between pulses, which means you don't have the helium ash problem that a tokamak might have, right?
That's right. We basically completely evacuate, pump down the chamber in between shots. So you'd have big vacuum pumps, ports to pump everything out in between shots. So what the ultimate limit on how, probably on how fast you can reparate is how fast you can evacuate between shots.
But you don't have much to remove, right? You don't have much stuff to remove because you only put a little bit of stuff in there.
Yeah, we only put a little bit of stuff in there, right?
Which is going to be eventually your xenon.
Everything. The only things we put in there are deuterium, tritium, and the liner plasma, which is argon or xenon. So it's all gas.
Yep.
So it all just pumps out. Yeah, there's nothing else in there.
And how perfect a vacuum do you have to get it initially? I remember when I was in grad school, I ran a scanning tunneling microscope at Berkeley, and undergrad actually. I ran a scanning tunneling microscope, and we weren't even in a complete vacuum. And boy, that was tough.
Well, yeah, that's because you have electrons that have to propagate through in order to do their scanning microscopy. And they won't propagate very far in air. Right? Yeah. For us, for PJMIF, you probably only need microtorr, 10 to the minus 6 torr, something on that range, maybe a little bit lower.
So it's still a big space. As long as you get pretty close to a vacuum, you're not too worried about other atoms getting in the way of your fusion event. Because that would be the concern.
The only atoms to get in the way, really, after you start firing, the only atoms to get in the way would be residual argon, which would be the material that would be the most that we put in, because you put in tens of milligrams of that, or actually grams of that for a total shot. But most of that will pump out. The walls, you'd clean the walls and you'd keep the walls pretty clean. Anything that is on the walls, like water and stuff like that, would, of quickly disappear after you start firing. So the only thing that's left is mainly the argon.
Yeah, you probably bake the whole thing before you even started it up.
Well, you'd pump everything, bake the walls, clean everything pretty well, and you'd have and getting down to microtor is not hard.
That's awesome. I mean, what am I missing here? What are some of the challenges that's going to take you guys, however long it takes to bring this to market? What are the main complications right now? Well,
probably there's a couple of main complications. The main thing is forming a liner that is sufficiently smooth. You asked about that earlier.
Yeah, I was worried about that.
From using a number of discrete plasma sources, somehow you have to merge all those to form a liner that's relatively smooth. Now, you can't make it perfectly smooth. That's not possible. So you have to make it smooth enough so that the residual perturbations in the smoothness don't cause deleterious instabilities to occur. The one in particular that we're concerned about is Rayleigh-Taylor instability, where you're trying to push a low-density gas with a high-density gas, and it'll tend to form fingers and ripples in the surface. But if you can do this fast enough, which is why we need the high velocity, then the hope is that won't occur. And as long as you have a smooth enough liner to start with, then and you don't have to compress too far, then that ratio of big to small, then you may be able to survive that. Rayleigh-Taylor wouldn't be a problem. So, and that remains to be determined. I mean, experiments down the road will tell that. And there's been some modeling that other people have done, not me, looking at that. And so that's an issue to be resolved.
And can you help smooth, can you ionize the gas and then help smooth the surface with just having someone coaxing magnets along the outside?
No, there's no way to put magnets in there. They'd be in the way.
Okay.
Yeah, that's not possible.
Yeah.
But it's already an ionized gas.
Right.
Yeah, that's what the plasma is. It's already ionized. Right. But no, you can't use coils. They'd be in the way. And if they were there in the first place, they'd disappear after the first shot.
I just kind of meant maybe it's like somewhere in the room.
You couldn't do them close enough to do anything. The second main issue is how to form the target.
Yeah.
Right. And so the target has to be magnetized, or the whole concept doesn't work. So by magnetized, I mean it has to have some embedded magnetic field that then increases in value and strength as it gets compressed down to a smaller size. And that's the way that that's what's called the magneto-inertial fusion part of the concept, is that it's inertially confined with a magnetic field, and that magnetic field reduces the electron thermal heat transport out of the plasma so that it stays hot as you're compressing it. Otherwise, if you didn't have the magnetic field, it would lose the energy faster than you could put it in, and you wouldn't get the fusion.
You can get that liner layer into it.
Yeah. So you have to do it. The whole process has to be really fast.
Yeah.
And you can't lose energy as it's being compressed.
So help me understand the magnetic property of that initial fuel plasma again. How does that occur? How does that get created?
Well, that is the issue still to be resolved. Okay. One of the earlier ideas that...
Theoretically, how does it work? How do you get a magnetic...
Okay, I'll tell you that. One of the early ideas was to use lasers and beat wave, have lasers that are just slightly different in frequency. So you get a
traveling wave of
a traveling wave, and that could drive electrons in the plasma, and which is a current. And you could therefore...
You physically rotate the electrons in the plasma.
Yeah, sort of. And you would drive them in a path that would make a current. And then that makes the magnetic field.
Yeah.
But it's not clear, whether that will work yet or not. or at least not well enough.
And you can't just line up all of these guns and then shoot them with at slightly different times, so it spins it as it comes together?
No. Slightly different times would just, the whole point is to get them at exactly the same time or you don't get the implosion. Now, the trick that we're going to probably try in the follow-on program is to embed a small magnetic field or a modest magnetic field in the plasma jet as it comes out of the gun.
How?
Just with magnetic field at the muzzle of the gun. And so if you do that, then you can hopefully then have magnetic field that reaches the center of the fuel, right? Or the target as it implodes.
Can you describe to me what is this magnetic field that you would embed in the fuel?
Well, it's basically a loop of current in the plasma that makes a magnetic field.
But the plasma, so your gun has a plasma in it initially that gives it its initial velocity.
Right.
Now you're shooting out your fuel, your deuterium-tritium combination, and as it passes through the muzzle of the gun, you're going to have some coil of wire on it that gives it an additional magnetic field. That way, when it reaches the center and it hits all the other parts of the fuel, that creates another, your plasma number 2. Now, plasma number 2 now has an embedded magnetic field that keeps your electrons in during that plasma so you don't lose heat and energy, and it stays there long enough. And then you have a third plasma wave that's the liner that comes in afterwards, and that's what makes the magic happen.
So
Did I get it?
Pretty much.
Love it.
The magic, I love it.
Oh, no, it's awesome. Cool.
Then,
How do you
and then
measure
the
all this?
third,
How do you measure all this? How do you measure what the magnetic field of a plasma is if it's moving out of the muzzle?
Well, there are different ways. You can use little coils of wire right at the exit of the muzzle of the gun, and you can measure it. It's called a B-dot coil, and you can measure the field directly. You can also do it spectroscopically and things like that. I'm not big expert on that.
Okay, sorry.
There are people who know how to do that.
Yeah. So third problem.
The third problem is just is the guns themselves. The guns are the driver for this whole thing. So the guns have to be able to accelerate ultimately, maybe 20 milligrams of plasma or more per gun at maybe 100 kilometers per second. And it has to do that with a compact jet coming out of the end of the gun. And it has to do that one time every second.
Yeah.
So you're going to have issues with cooling. You're going to have to cool the gun. And you're going to have problems with actually achieving those parameters that I was just telling you. Those are challenging things. They appear solvable, but they're going to be challenging to do.
Materials.
Yeah. But it's the rep rate that will be the hardest thing to probably get.
What temperature can they operate at? These
You
guns?
mean the guns themselves?
Yeah, the guns themselves.
Well,
could you operate them at 500 C, and that way you can just use the same coolant as you're using to remove the heat from your entire system?
No. You wouldn't use the same coolant as for the fusion part. This would be a whole separate loop, it's unclear what the material you would use for the coolant. Maybe it's water, maybe it's some other fluid of some kind. But you probably don't want it to go above a few hundred degrees C.
Yeah.
But if you do that, then you have to deal with various seals in the gun that usually are like rubber, right? For like the gas valve and things like that. And so you can't let those get too hot.
Yeah.
Everything else is going to be ceramics and advanced, refractory metals and, copper and things like that for the most part. But the seals will be a bit of an issue. Or you have to redesign the gas valve to not need rubber type seals.
Now, these guns are exposed to the same vacuum as the main chamber. So the guns have to be maintained at a vacuum, essentially. Got it.
Yeah, the guns are at the same vacuum as the chamber. And So they have all the sealing issues and things like that you would have to deal with for that. But for the most part, the sealing against the vacuum isn't much of an issue. That's relatively easy to solve. It's the gas valve that'll be, because that's a dynamic system. It has to open and close one time every second.
Yeah.
And so that might be challenging to do. And it's got to operate like that for 100 million shots.
Yeah. Yeah.
So
what's going to move this technology forward? You mentioned you're on a couple of grants right now. Is this with the ARPA-E program?
Right.
Love ARPA-E.
Yeah, absolutely.
ARPA-E is like
the
greatest thing that's ever
fabulous.
existed, right?
That's right. Really.
So
since sliced bread, anyway.
Yeah. So you're on, I think, what would they have, like an alpha project or something?
We're one of the alpha
And is there going to be another?
Well, there is another program that's kind of nominally called beta,
okay.
But that's not its official name. But there was a workshop just a couple of weeks ago in San Francisco which is their required workshop to set up the follow-on program. And Scott Chu is going to be running that program. And so they're setting up right
Scott's
now.
The man.
Yeah. They're setting up the requirements for that program now and the scope and all of that. And so hopefully that program will get approved. It's still in the design planning stage now.
And then the idea is, so hopefully that program gets approved and then you guys win a grant. And then what's the first thing that you do to test? Or to move this technology forward?
Well, the first thing is to start working on the target guns. That's the key next step.
And where do you guys get a hold of deuterium, tritium to practice with?
Well, you just buy it. You can buy that from...
Tritium?
Well, not the tritium, the deuterium.
Okay.
We won't deal with tritium anytime in the near future.
Yeah.
We couldn't do that here or even easily at Los Alamos.
Not at Los Alamos?
No, I mean, eventually, but not at the PLX facility that we're using there now.
Yeah.
And it's not necessary. All we need, we could just do the experiments with deuterium now, and that gives us everying we need.
So it would be a deuterium fusion event that occurs?
Yeah, you'd probably get some, but like I say, we're not going to probably make neutrons in the next beta program, so-called beta program, because we won't get to the parameters necessary for doing that. Except there might be a few, a small number, depending on how high a density and pressure and temperature we can get in that imploded process.
Well, we'd love to see that because that would be
We would love to see that, but we don't want too much coming out now because we want to use the same facility we have now, which can't handle too many neutrons. Right, yeah. I mean, that's the safety issue there. So once you get to the point where you want to make a lot of neutrons, you're going to have a different facility for that.
Yeah.
So that's down the road. We're focused right now totally on
that's a good problem to have.
That'd be a great problem to have. Right now, we just want to demonstrate making the target and then do the liner implosion on that target. That would be the second part of our proposed beta program.
What would accelerate your guys' progress the most? If we had, if we were decided to really take this climate change problem seriously and just start pouring hundreds of billions of dollars into all clean energy technologies, how would you guys apply that to bring this technology to fruition in the next, let's say, 5 years instead of 15 years? What would you do?
Well, I don't think even if you throw huge amounts of money at it, I don't think you can solve it in 5 years.
We can't just hire more people, run more experiments.
No, because a lot of the work has to be done in serial. You have to get the various stages. Now, what you can do is speed up the process. Right. Instead of 15 years, maybe you get it down to half that.
Yeah.
7 or 8 years. But 5 years seems a little aggressive, ambitious.
Good. Yeah. That's what we want. We got to save the planet.
Yeah. And so funding is the real issue there. You need more people. There needs to be a lot of code work.
Are there
numerical simulations of all this? And we need to develop a lot of the technologies, like for the gas valves, igniters, and capacitors and switches and things like that are needed for the subsystems of this. A lot of that work could be done in parallel while you're developing the plasma implosion process itself. But there's a limit to how much obviously can be done in parallel. But you could speed things up dramatically. That would just require money and people.
And what about the talent out there? Are there enough people who understand the fundamental science, or do you only really need a few people who understand the science and then everyone else is a materials person?
I think there's plenty of people out there. I mean, there's a lot of smart scientists in the community.
Yeah.
And so I don't think that's an issue. It's a matter of supporting them.
Yeah.
Yeah.
And then how do you think this technology holds up against the other approaches to fusion?
Well, it has certain advantages. It has some disadvantages. The advantage we view it as is that you have the magneto-inertial fusion in general. I mean, has the potential of getting to a fusion reactor a little bit faster and potentially cheaper than the tokamaks. The tokamaks, I'm sure, will eventually work, but they're huge and they're very expensive. They take many, many, many years to build and stuff. Whereas the systems that we're working on and some of the other alpha winners, the different approaches, have the potential to get to break even maybe faster and with less money. So from that point of view, you can do the development, the R&D development on a faster timescale and lower cost.
And what about fundamental physics challenges? Where does everything line up?
Well, I think they're all very similar in fundamental physics challenges. Our challenge is not so much the physics, but in some ways it's the physics, but in many ways it's the engineering of being able to make the systems do what you want them to do. The tokamak people have the same problem, but they have a lot of other true physics issues, disruptions and things like that they need to learn more about the physics. We need to learn more about the physics of the implosion process itself. So that's a real physics issue, is, trying to avoid the Rayleigh-Taylor instability. Is that possible? And can you actually make a smooth enough system that will implode and get what you want out? But fundamentally for us, it's more work in the drivers, the guns, that kind of thing. That's where really most of the work will eventually go, and most of the money will be spent in development, is making guns that can do this work.
Yeah.
And so I think of that partly as physics, partly as engineering.
Yeah. Is there any complications in computerized control, or is that not a concern?
No, the computerized we'll need that, but that's not really
nothing hard about maintaining stability or anything.
Well, it's not that it's not like we get feedback control. Like tokamaks, you can have feedback control because they're long pulse items and eventually would be steady state or close to it anyway. We're not anywhere close to that. Our whole experiment is over in tens of microseconds, right?
Awesome.
And so there's no feedback control for that kind of time scale. You have to get everything right in setting up your initial conditions.
Yeah.
And so you may have some feedback control in terms of controlling the subsystems, but not during the shot. It is for adjusting things from one shot to the next.
And what's the smallest one of these reactors could be and still work?
That's actually a good question, and I'm not really sure what the answer is. It's hard to imagine it less than 50 megawatts.
50 megawatts, and that would be the size, all the equipment would fit into the size of what? A basketball gymnasium? What would?
Let's see. Yeah. I mean, that's approximately correct. A nice basketball gym. Depends on what you mean by gym or arena.
Yeah, right. What about the court? Could it fit on the court, a whole system like this?
No, not completely on the court, but maybe not much bigger. Because you're going to have lots of capacitor banks that surround this system, and it's unclear how much space that will take up. I mean, it's not ridiculous, but it'll be... it'll surround the whole system, right? The actual device itself could only be maybe 10 meters in diameter. So, it's not that big. But it's all the support systems around it that would require more space.
Cool. And as we wrap up here, maybe just kind of, how do you see the future? 5, 10, 15 years, let's say 15 years from now,
I think in 15 years, someone will have reached break even. Whether it's us or somebody else, that's hard to say, but someone will have reached break even.
Awesome. Doug Witherspoon, thank you so much again.
Yeah, it's been a pleasure.
Yeah.